Now the question is, can we apply that trick that worked so well for dissolving traffic jams on freeways in that simulation that I showed you? Can we apply similar principles also to congestion in urban areas? And of course, there are these noble goals of traffic planning, you know, better mobility, less pollution, less noise, less traffic, more sustainability, and so on and so on and so on. And so this is how we imagine it to look like. And in fact, it often looks like that. Very different, a lot of congestion, many cars, standing each other in the way, urban gridlock, and so on and so on, right? And here is a movie that I always found very inspiring, which shows self-organized traffic in a highly diverse traffic situation. Many different participants, and nobody almost ever has to stop. And that's kind of surprising, but you know, if you look at this more closely, then you find that we have a particular design here. We have a unidirectional flow of traffic in the front. In the back, we have the opposite unidirectional flow. And in the middle, there is actually a buffer which allows every traffic participants to adjust the speed in such a way that there would be a gap to cross the flow when they arrive. That's all, you know. It's a particular design that supports self-organization. And of course, you know, people do honk, and there are accidents sometimes, but the question, could we learn from the principle? And that was basically our inspiration. And we wanted to come up with a new kind of traffic light control that was made to adapt to complex street networks, to traffic disruptions, and particular events. And in order to get there, we first had to represent the traffic network and traffic flow in a model. So we had to abstract the problem. The road network is being represented by a graph where the links have certain kind of features, you know, lengths, capacities, storage capacity, flow capacities, and so on. And along the links, we would assume a certain traffic flow dynamics, which is actually given by the Lytle-Wissem model, which is basically using the continuity equation from physics to model the flow of vehicles. And here, the fundamental diagram has been assumed to be triangular for a city traffic flow, which is, here is the speed limit, and that's the minus 15 kilometers an hour that we had before, okay? And basically, it assumes that if there's a red traffic light, cars stop. And if there's a green traffic light, they drive at their desired speed. And then with a certain delay, other cars will follow. And as you can see over here in that illustration, right? Now, the interesting point is it's possible to reformulate the partial differential equation of the Lytle-Wissem model in terms of a delay differential equation. And it's possible to determine everything which happens within the road section from the flows that go into the road section and out. And also the location of the queue of vehicles that forms behind a red light. That means the jam front or end, in a sense, jam end. And its location over time can be calculated from those in and out flows. I mean, arrival and departure flows, okay? And then we have to see what happens actually when those different road sections meet each other at intersections. And of course, there also needs to be a flow conservation, something like the Kirchhoff's law needs to apply. So the sum of flows needs to agree. and so on and so on. And then basically we have to model the intersections, right? And now the interesting point over here is there are several minimum functions, right? And it means that, oh my God, minimum functions are really not good for us, right? It basically means that whenever I do a mistake, the minimum flow will result. Well, I'd like to have the maximum flow, right? So all the traffic flow control in the city is basically about avoiding switching on those minimum functions, okay? And how are they switched on? So take this example over here. We have an inflow, 2 outgoing roads, but once one of those roads is full, then the other one is blocked as well, right? So the minimum function comes into play. That's all which is behind the minimum function, basically. Then we have to model flows on each intersection. Of course, each intersection could be different depending on, you know, how is flow straight, right, left, organized, and things can be different for every intersection almost. And now we have to talk about traffic lights. And the traffic lights will basically introduce a certain factor which is basically changing the throughput. If we have a red light, then obviously the throughput is being set to 0. If we have a green light, the prefactor is just 1, okay? And now with the specification of the maximum throughput, we can eventually simulate traffic flow in a road network. And now the tricky part is, how do we get the green waves that we'd like to have? Green wave means that cars wouldn't be stopped many times, but they could pass several intersections without stopping. And in fact, a lot of things can go wrong. If we have a non-optimal phase shift, if we have different cycle times, if we have stochastic switching, you know, we would always basically get additional delays, additional stops, and getting it right is really extremely difficult, in particular as the delay times between different intersections depend on the number of cars in the queues forming behind red traffic lights. That means the delay time is a dynamic variable, and the delay time in one direction of a road section is different than in the other direction. It's really an absolute nightmare, an absolute headache to come up with an optimal traffic light control. And you need to make some simplifications. And typically what people do is they try to come up with an optimal periodic service at an intersection. And then they try to synchronize the cycles of neighboring intersections, right? This is how it works. But non-periodic solutions are basically thrown away. The only thing that they do is they adjust the green time, they make it a bit longer or shorter, but they don't always change the order in which different road sections at an intersection are served. Now, we have taken an entirely new approach. We've been inspired by the pedestrian flows at bottlenecks. And what you see here is an oscillatory flow. There's no traffic light here, no policeman, no rule. It's just the buildup of pressure that creates this oscillatory flow. And so the idea was intersections are also actually bottlenecks. And if we would come up with a suitable pressure principle, the pressure would basically create self-organized oscillatory flows, and we could use those to define the traffic lights. It means the traffic flows would control the traffic lights rather than the other way around. That was the revolutionary idea. And it turns out if you do that well, with a short-term prediction of flows incoming from neighboring intersections, but without a central traffic light control, you would get the self-organized formation of those green waves. It looks absolutely great, I would think. Just the point is, no, European cities don't look like this. And then the question is, how well would that principle work for really messy cities, with irregular road networks and stuff? And so what we've done is we have compared 3 different road net control approaches. And the left one assumes the traffic control center, which collects as much data as it can about the traffic situation, then tries to optimize in real time, but is limited by what can be done because of the NP-hard optimization problem, and then imposes the best found solution on the entire city like a benevolent dictator, right? But in particular, it tries to coordinate between different intersections. Now, in the middle, we have a much simpler approach. We assume bottom-up self-organization. Each intersection separately tries to minimize travel times. That's it. Just considering the inflows into the neighboring road sections. So it's like every intersection acts like Homo economicus, does locally the best, but doesn't care about others, okay? And we would think that's not coordinated, can't be that good. And then on the right, we do the same thing apart from when the traffic jam grows big. We would first clear the traffic jam before we go back to travel time minimization. This avoids spillover effects. It means it's nice to the neighboring intersections, and that's why we call it other regarding self-regulation, okay? We would think because it's less selfish, it's going to be less effective. And let's see what really happens. Now, the red line represents what we find for top-down control. As the capacity utilization goes up, the queue length of cars behind the red light increases more or less linearly. That's kind of what we expected to happen, right? Now, let's see what happens for the selfish optimization and the Homo economicus approach. And it turns out to be much better over here. Much less queue lengths because we're not waiting to switch green when the cycle foresees it, but whenever a new car arrives, it will get a green light right away. But eventually more and more cars come in, and some come in at the same time, and then you cannot prioritize, and eventually you see the queue length explodes, and that's it. And then the traffic control center says, see, that's why you need us. So we can say Adam Smith's invisible hand, self-organization works fine over here for low capacity utilization, but for large capacity utilization, it fails. Now let's see what happens for the third approach, which, hey, surprisingly is actually better all the way. That means this other regarding feature is actually benefiting not only the neighboring intersections, it's if everyone does that, it's actually good for everyone. And so we can make the invisible hand work, and bottom-up self-regulation can actually outsmart optimal control attempts, okay? So now the question is, how well would that work in real traffic networks? Okay, so let's have a look, for example, at the city of Dresden in Germany. I can see it's a typical irregular road network as it has grown over times of history. And so when we talk to the traffic control center in Dresden, they said they're pretty happy with their traffic control, but not there. And even though they've bought a state-of-the-art control, I mean, there was a competitive bid, and all companies who wanted to sell their software could participate in this. And they've been taking the best bid. I think it cost several millions, if I remember well. They were not fully happy, even though I should say this traffic light control produced, as far as I know, a greenway for traffic flows. And it was also adaptive to changing inflows. But the thing they couldn't do at that time was prioritize public transportation. So they wanted to give trams and buses priority when they arrived. But if they would do that, they would basically interrupt the green waves and destroy them in a sense. And that would create monster traffic jams within a very short time period. And that traffic jam would stay for hours, you know. So they couldn't prioritize public transport. Now, our approach was different. We wouldn't just give a green light to the tram whenever it arrived. We would give instead the tram a weight of 10 vehicles. And that was basically it, you know. Then we let the self-organization sort it out. And that's what we got. The state-of-the-art control that they bought before we talked to them does the green waves, as shown over here, right? This is what our system does. It also produces green waves, but not as regular ones. It's using gaps in the flow as opportunities, as I said. And now the question is, how is this actually performing? Now, it turns out public transport benefits a lot, but not at the cost of motorized traffic. I mean, even motorized traffic still does a bit better. And also pedestrians and cyclists actually have better waiting times. And so summarizing up the results, we can say that everyone has gained. And this would be good for the environment too, because there's less congestion, less time spent in the roads, less CO2 emissions, less noise, and so on. One of my PhD was looking into this, during the lockdown. He was starting to compare machine learning based approaches, which started to compare that with that method of Stefan Lemmer and myself, which he calls analytical plus approach. I mean, the plus is for the stabilization part of it. And it turns out it achieves the best possible performance without learning. While the machine learning takes, 150 and if improved half as much, but still a lot of learning episodes in order to achieve the same level that the self-control approach reaches right away.